Oh, good morning, everyone. Yeah, sorry about yesterday. We had a problem in our region with power, so we'll just continue from where we left last week. So we were talking about the coaxial connectors that you need for high frequency applications, and we were talking about the power handling capacity being more important for microwave systems because most of the times the power that we'll be encountering in these particular systems will be large. So we did talk about the issues in TV systems. Usually you are using an antenna to trap the electric field intensity that has been launched into the sky, and you are trying to get it through an antenna that is usually short, and therefore the fields will be very small, especially for TVs. You'll get a field of about 5 microvolts per meter, and with an antenna of about, say, something like half a meter, you can see that the voltage that you're dealing with is very small. And therefore, what you're trying to do is to try and maximize the signal, the received signal, to try and reduce the SNR, or the signal to noise ratio. So connectors are used in pairs, and most will possess certain characteristics, such as, say, they must have low standing wave ratios because you don't want to reflect the signal that you are receiving. You want it to be absorbed into your system as much as possible. Then they would have higher order mode free operations at high frequencies because most of the time you'll be terminating the particular system you're connecting to a single impedance. And we say that when you have higher modes, then if you want to receive them, to absorb them in your load, then you must terminate them properly with the correct characteristic impedance. So for high repeatability, because connectors will often be connected and disconnected, especially in a measurement lab or system. Then the high mechanical strength, we don't want any wear and tear because of the many disconnect cycles. And therefore, the first one we look at is what we call the type N coaxial connector types. And the type N was developed in 1942 by Neil, and they are usually come in sexes. That is, you have a male and a female connector, and these must thread together. So the female has an outer diameter of about 0.6 to 5 inches, and hence the connector will operate up to about 11 to 18 gigahertz with a standing wave ratio of approximately 1.07, which is very good for that particular kind of range. The sub-miniature type A adapter, or the SMA adapter, is what you're going to meet many of the times when if you're going to have to work on a project in high frequency. Most of the time you'll just get these SMAs. They are the ones which you can get locally quite easily. And this was developed in the early 60s. So the fabrication motivation was motivated by a requirement for a light and compact connector, and the female would have an outer diameter of approximately 0.25 inches, so that the Fmax would then be about 25 gigahertz. And this is important, especially for the measurement systems in common ranges up to about 26 gigahertz. So the connector is most widely used at microwave frequencies, and due to the great demand of this type of connector, there are two other variants of the same connector that have been made. One is called the K connector, developed by the Maori company, and this has an Fmax of about 40 gigahertz. the 2.4 millimeter connector developed by HP or Hewlett Packard, which was later changed to Agilent. And now I guess it's called Keysight, and with an F max of 50 gigahertz. The reason why we are trying to push and higher frequencies is because in measurements, you'll find that we are using the spectrums at higher and higher whatever frequencies are becoming available. Today, we'll have, like, say, for example, the anti-collision radar in cars will be operating at about 77 gigahertz, and there is also another part or another band around 94 gigahertz. And today, the drive is to try and go into the terahertz kind of ranges in applications, and therefore you need connectors for these measurement systems. Of course, in many cases, you'll find that the coaxial lines will not be used at those frequencies, and most of the measurement equipment will be using the waveguide interconnection. The scale SMA, which is similar to the SMA in design, but it has a smaller size, with the female having an outer diameter of 0.192 inches and has an F max of about 38 gigahertz. So the APC7 or Amphenol precision connector has a useful frequency range of up to 18 gigahertz with an SNR, or with a standing wave ratio of less than 1.04 over the whole range. And this has a sexless connector, that is, the two connectors do not thread together, but they butt their contacts. That is, the surfaces are pressed together, okay, for both the inner and outer conductors. So the BNC or Bionet Navy connector is what you have met many times in our labs, with the ones we use for the oscilloscope connections. And we have another one which is threaded, and it's called the TNC or the BNC, threaded BNC. And these enjoy common use in at RF and IF frequencies, but never at high microwave frequencies, because, like we said, the coaxial cables must be very, very small if you are going to use them at high microwave frequencies. And this is the ubiquitous coaxial computer network connector, or the normal coaxial cable or probes that we use in the lab. So we now look at what we call the waveguide cavity, and we looked at the rectangular waveguide cavity, and now we look at the circular one. And for simplicity, we'll consider the TM01 mode in a circular waveguide of a radius A at cutoff, so that there are no variations in the Z direction. So the ends of the cavity are shortened by conducting plates at distances D, which are less than 2A apart. That is, we don't want them to be to have a variation in the Z direction of the fields. So the fields is that the cavity will then be the EZ, okay, for the TM01, and we have for that, for a particular value, that is the KCR. KC is given by 2.405 by A. This, you remember, we said was the first root, the first root of the J naught, or the base of function of the first kind of the zero, okay, had a zero at 2.405, which is the first one. And then we have the H5, which is circumferential, and it has a value of C naught by eta naught, where the 2.501 is for the J1. That is where J1 is simply equal to the derivative, or the first derivative of J0 at the J0 value, where n is equal to 0 for this particular case. So the electric and magnetic fields are hence in quadrature time phase, and this therefore result in no power loss in the cavity walls. So for a circular cylindrical cavity of radius A and length D, the energy stored in the cavity for the TM010 mode is then given by U equal to twice the energy stored in the electric field, because we have already seen that the energy stored in the magnetic field and the electric field are actually equal, and therefore we can just the total energy stored be twice one of them. And this can be given as the epsilon naught by 2 and the integral over the volume of the magnitude squared of the axial component of the electric field intensity. And we get a value of about pi epsilon naught multiplied by the length of the cavity and multiplied by the constants, the amplitude constants, multiply the base of functions. So the time average power loss due to dissipation in the wall due to finite conductivity will then be given by P average equals to a half multiplied by the modulus of the JS. We remember that JS is equal to the cross product of the normal component or the normal vector from the wall by the magnetic field, and we multiply that one by the surface resistance per square, which is Rm, and we get a value of 1 by 2 h phi squared and multiplied by Rm. There will be radial currents, JR, on the surface plates, and uniform axial surface currents, JZ, on the inside of the cylindrical walls. So, and therefore, we get a total power loss that is given by Rm, given by the radial losses due to the radial currents in the caps, the end caps on the cavity, plus the loss in the circular walls of the cavity. And once we deal with these values, we'll get a value of the integrals that nature. So, in other words, the power loss will be given by that expression where we have the dimensions of the cavity, that being the radius and that being the length. And therefore, the Q is just going to be given by the energy stored divided by the value of the energy lost, and we get a value of that. And we note that this, because of the integrals, we are integrating base of functions. These are special, values that we have given here for you, so that you can see how to integrate that. But many times we'll see that for circular waveguides, the integral mathematics is a little bit involved, and nobody will ever try to ask you to deal with it. This one you will meet in the industry when you start working, and you can always use the handbooks, so to speak. So when Rm is given by the root of pi f mu naught by sigma, where sigma is the conductivity of the wall material and mu naught is the conductive permeability for the walls which are assumed to be non-magnetic, therefore they have permeability of free space, then we can see that the cutoff frequency for the, not the cutoff frequency or the resonance frequency for the TM010 mode would then be given by that value there, which is 0.115 gigahertz. So, an example then. A hollow circular cylindrical cavity resonator is constructed of copper such that its length d equals its diameter 2a, and determine A and D for a resonant frequency of 10 gigahertz for the TM01 mode, hence estimate the Q. So we have that FTM 010 has been given by that value, and we get a value of 10 gigahertz, and hence A would be about 1.15 centimeters and D 2A, which is 2.3 centimeters. Rm would be given by that value 2.6 or 26.1 milliohm and per square, so that the Q is just going to be given by about 11,580. So if we were to compare the circular and rectangular resonators or cavities with comparable size at the same frequency, we'll note that the resonant mode at frequency for 10 gigahertz, and that for the TE101 mode is the 10 gigahertz, then the dimensions are as follows. The radius here would be 1.15 as we have computed, and the length would be 2.3 centimeters as we have computed. For the rectangular cavity where we have A equal to B equal to D, that is a cuboid, then we'll get a value of 2.12 centimeters. And we see that this is going to be much smaller than that. So if we were to look at the volume, we see that the volume for the circular cavity will be a little slightly larger than that one of the rectangular cavity. And the total surface area of the walls, you'll see that this one has a smaller surface area and that has a higher surface area. And therefore the Q is going to be given, and the Q we saw was slightly less for the rectangular cavity, and that for the circular cavity will be that. And therefore you find that most of the cavities that you get in the industry will have such kind of stuff. So for the rectangular cavity, the one which comes into mind is a microwave oven in the house. Okay, the microwave oven is made as a electromagnetic cavity, where the cavity we are dealing with is, of course, where you place your food for warming or cooking. So this, we can say that the rectangular and circular resonators will have the same volume, but the total surface area will be slightly larger for the rectangular and cavity, and therefore we get a lower loss, a lower Q because of the higher losses, because of the volume to surface area ratio. So we now show how we can solve the base of second order differential equation. This is given here for you as a completeness so that we can understand where the J or the base of functions come from. So this I'm sure you are going to cover also in mathematics when you deal with power series solutions. So it's called, I think, mathematical methods or something like that in fourth year, in your, I think, the second semester. You must be doing that now. So recall that the radial differential equation, okay, for the circular waveguides was a base of function, was a base on second order differential equation, and we said it was whatever, it was a standard form. So we let that the solution for that equation be R of R, okay, and this is going to be given by KCR all raised to nu, and we are assuming that it can be expressed as a power series, okay, in terms of the argument Kc of R. And therefore you can write it as the Kc of R raised to nu, where nu is just a value or an exponent that we shall determine when we solve the problem. And therefore, and this is multiplied by the sum from L equal to 0 to infinity over coefficient C of L, multiplied by that KCR raised to L, and equal to, we can always multiply this one through, and we get about an M plus V, and we note, or we insist, that C naught, that is the first coefficient for L equal to 0, is not going to be equal to 0. That is, it's going to be an arbitrary value that we can always determine. This will be determined by the boundary conditions that our solutions or the solution space has. So on differentiating this expression term by term, you can see that the dr by r is going to be given by that expression there, and the d2r by r dr squared will be given by that expression there. So if we take those values into the differential equation that we already formed, we had a d2r of r squared and a dr of r squared. So we'll put those ones in here and we'll get a value of that nature. Remember, there was a 1 by r dividing somewhere and 1 by r squared dividing at the other end. I don't know whether we can go back, it's a bit far, but you can recall that, or I leave you that to look at later. So if we divide through by Kc of r raised to nu, we'll get the following expression. And we can therefore write it, that is, we can connect these ones together, okay, collect them together, and we get a value of L into L plus 2V multiplied by Cl of KCr raised to L plus the sum of Cl of KCr and L raised to 2 equal to 0. And therefore, for this equation to be true for all values, then we must set the coefficients of the powers of Kc of R equal to 0 for the appropriate cases. So the first thing we do is that we set the coefficients of Kc of R raised to L, V, that is, not P, this is V, to 0, so that for L equal to 0, we can then have that C naught into V squared minus V squared is equal to 0. And for L equal to 1, we have a value that 2V plus 1 into C1 is equal to 0. And therefore, we must have that C1 is equal to 0. And for a general L greater than 2, we can have a value of L into L plus 2V into multiplied by CL plus Cn minus 2 is equal to 0. And since C1 is equal to 0, then we must have Cl equal to 0 for all other odd, for all odd values of L. They always go to 0, and those ones for the even numbers will be related to the C naught. And for L even, we then have that Cl equal to 1 over N into L plus 2V and Cn minus 2. Or in other words, the C of 2L is going to be given by that value there, which you can always reduce it to that form. So a solution for the R is therefore going to be given by that equation there, which we started with, that is the solution, and we multiply that one through. So it is usually usual to normalize the solution by setting C naught equal to 1 by 2 raised to nu multiplied by nu factorial, because what we want to do is to make sure that the only thing we now need to do after we get the solution is just multiply by an amplitude, because we know that that one is going to be equal to unity, so it's normalized to unity. And therefore for P, which is an integer, the solution can then be expressed as that value there. Now we have N equal to 0, and we get a solution of AN, JN, KCR, and the JN, KCR is of course given by that value there. So the base of functions of the first kind and even order are then shown below for the first three integer orders. That is, we have J0 of KCA, we have J1 of KCA, and J2 of KCA. What you will notice is that although as we go to higher and higher orders, we start getting that the roots are not evenly spaced along the real axis, like in a sinusoid, so to speak. They are separated, and they become wider and wider as we go along the KC multiplied by A axis. What this one looks like is like a damped sinusoid, like that you have dealt with in resonators, and you are going to get a similar kind of equation, especially when you deal with FM modulation, that is the frequency modulation signals in whatever telecoms. You are going to get similar kind of values. So the choice of the value of C naught has arisen from the earlier studies of base of functions, in which the Jnx was taken as the coefficient of the variable t raised to n in an expansion of the equation exponent x by 2 t minus 1 by t. That is, we have that value there and expand it in a Maclaurin series, and we'll get a value of that nature. And then when you deal with it, you'll get the value of the Cn. So the function exponent of x by 2 t minus 1 by t is called the generating function of the first order. So the Bessel differential equation is a second order differential equation, and therefore we expect two solutions. So the second kind, that is the Bessel function of the second kind, an order n, or the Neumann function yn of KCR will be given by that expression there. The reason is, most of the time, you'll find that the Neumann function of the second kind is indefinite at r equal to 0. And when we have the n integer, this becomes a very problematic issue. So thus, the general solution can then be expressed as r of r equal to a n j n kc of r plus b n y n kc of r. So we note that yn of kcr will go to 0 to infinity at r equal to 0 and must be excluded whenever the problems that we are solving include the origin. Say, for example, a hollow circular waveguide, the center will be part of the region of interest, and therefore the y of n must be set to equal to 0 because r equal to 0 is part of the solution space. Okay, so it will not be a valid solution, and therefore for the hollow circular waveguide, then we must have that being the Bessel function of the first kind being the only solutions. Now, if we have a coaxial cable, we'll find that if the inner conductor is a good conductor, that is very good conductor with conductivity tending to infinity, then it has taken out the r equal to 0 for us, because the electric field inside a conductor will be 0. And therefore, since the r equal to 0 has been removed from the solution space, then the Bessel function of the second kind must be part of the solution that you'll obtain. So in the study of hollow waveguides, like I've said, the origin is included and the Neumann's function is not valid. And if the entire range of phi is not involved in the solution, that is not the whole circumference is involved, such as in a wedge-shaped waveguide, then the v is not an integer and r would have values of that nature. So some problems will be simplified when jv and yv are linearly combined to form the Hankel functions of the first and second kind. Hankel functions are generated just, if you recall the Euler's formulae for trigonometric functions, where we say that for cosine is e raised to j theta plus e raised to minus j theta by 2, and the sine is given the same. We can also have the same kind of functions looking like that. So we have the Hankel functions of the first kind given by the Bessel function of the first kind plus the j multiplied by the von Neumann's function or the Bessel function of the second kind. And the Hankel function of the second kind will be given by the minus sign. So this one corresponds almost to the sine, the e raised to minus j theta, and that appears to look like e raised to j theta, okay? But that is just in form, not the equality. And therefore, as kc of r goes to infinity, we find that the first kind, the Hankel function of the first kind, approaches a sinusoid that is shifted in phase. And that of the second kind has a negative value of kc raised to that. If you can notice this first part here, which is related to the spatial direction, we see that this is a wave that would be propagating from infinity towards an origin of a sphere, so to speak. While that one is a wave that is propagating away from a point spherically along the radius. And therefore, the Hankel functions of the second kind have become useful in the study of radiation or radiated fields from an antenna, so to speak. So the large argument approximation for the Hankel functions are useful in the study of radiation and the scattering problems. So note that HV1, or the first kind, for large kc, is a spherical wave propagating inward from toward the origin, and that will be propagating away from the origin. So when kc squared is negative, the solutions of the Bessel functions, the differential equation, will then have a value given by IV, given by the zeta of R, where zeta now is to represent the negative value of the square root of K, or the Kc that you have there, which is just JKCR. And the Kv is given by that. Now, IV and Kv are called the modified Bessel functions, okay, of the first and second kind. These are important, especially when you are dealing with round conductors that you'll be using in, say, electrical wiring and the likes. So for zeta R going to infinity, the values have the following expressions, where we see that for IV of the first kind, this will be increasing with the radius or the distance from the axis, while that will be decreasing. And therefore, we see that this one will not be a very useful function for the study of round conductors, but this will be applied. So that will therefore exhibit an exponential decay, and this is the characteristic of an evanescent wave, and is useful in the study of the surface waves in road dielectric waveguides, especially like the fiber optics. And that brings us to the end of that particular part of these functions. Now, we have talked about the issues that appear in the waveguides and the transmission lines. And now there's a useful thing, or a very important phenomenon, and this is that of attenuation. Now, we will first look at the attenuation in the parallel plate waveguide, which we know that its fundamental, or the dominant mode of operation, is the TEM, because we have two conductors. But if we were to operate our guide at very high frequencies, such that we start, the waveguide modes now start fitting between the plate separations, that is when the plate separation is at least a half wavelength, then we'll have to start dealing with the waveguide modes. So in a guiding structure, the losses may arise from two different points. One, we may have conductors that we've been assuming to be infinite or perfectly conducting, therefore having a conductivity that is infinite. The conductivity will be finite in all practical guiding structures, okay? That is, sigma C is going to be less than infinity. And two, we'll have lossy dielectrics, because we have seen that in many cases we may have a non-magnetic dielectric, in which case mu will just be the permeability of free space, or we may have a magnetic or slightly magnetic material, and then we'll have magnetic losses as coming from the polarization of the dipoles. And the same thing would happen for the electric permittivity, where we have included also the finite conductivity of the non-zero conductivity of the dielectric to lump them together with the polarization or damping effects that we have already met in the last semester topics. So the losses will then modify the distributions of the field distributions between the plates or in the guiding structure from their lossless value. But we can expect, in many cases, if the losses are low, the transverse field distribution may be expected to essentially remain unchanged, okay, for those kind of things. And this will be valid in most practical guides using conductors with very high conductivity. Say, for example, copper with about 5.8 times 10⁻⁷ Siemens per meter. That would be a very nice value, and we'll see that the displacement current in copper is going to be very small. So propagation in a lossy guide will then be accounted for by using a complex propagation constant, which we shall call gamma equal to alpha plus j beta. And this, you should remember, it's a gamma that is, it's only unfortunate it looks like the other one we were using before, when we were dealing with the waveguides, when we say that the gamma there was also something like, you know, we could get it as being just purely real or being a complex value. So it's just, they just look alike, but anyway, the propagation constant, because of the losses, will be given by that. Okay. So the alpha D and the alpha C are the attenuation constants contributed by the finite conductivity of the walls, that is alpha C, and alpha D is contributed by the finite conductivity, the non-zero conductivity of the dielectric. So we'll consider the attenuation in transmission lines and waveguides to illustrate these losses. So the transverse electric and magnetic field intensities are given by that equation there from the reduced Maxwell's equations. This, we just write them by to repeat. And a guiding structure with more than 2 conductors will then support the TEM mode of propagation as the fundamental or the dominant mode. And 2, it will support TE or H mode propagation and TM or E mode propagation as well. And the propagation constants are different for TEM and TE-TM modes. And if you recall, we saw that for TE and TM modes, the propagation constants are the same. Okay? So the electric and magnetic field intensities in the parallel plate transmission line of a plate of width W for the TEM mode and plate separation B would be given by ET, where we are assuming that our field is polarized in the Y direction, because if we were to say that B is the separation of the plates, then from circuit theory, we know that the field will always go towards the shortest distance, and therefore the first one that will be generated will be that with an EY, okay, rather than EX. And therefore, the H of T is equal to Z cross E of T by eta, where eta is the characteristic or the intrinsic impedance of the dielectric between the plates. And we see that the value is just going to be the minus of Y of X, that is minus of X EY divided by eta. So the time average Poynting vector is therefore going to be given by a half of the real part of E of T plus E of H of T conjugate, and you get a value of Z cap EY squared over 2 eta, and this is a lossless line. Now note that the wave is assumed to be Y polarized and propagating in the positive Z direction with a propagation factor of the value exponent of J over the T minus gamma Z. So in a low loss line, the attenuation constant due to lossy dielectric would be given by the following function, that alpha D is approximately G prime by 2 multiplied by Z naught. Remember, the G prime comes only from the dielectric. So if you recall our transmission line, the expansion we made, we had an R divided by Z naught, R prime by Z naught, but that was a series resistance. Okay, that series resistance comes from the finite conductivity of the conductors themselves. And therefore, for the dielectric, this is the part that is contributing to that loss, the attenuation constant. And therefore, that can be given as omega prime, double prime by 2 eta. The attenuation constant due to the skin effect in the conductors will be given by A of C equal to R prime by 2 Z naught equal to 1 by B and the square root of Rm. That is multiplied by Rm. And hence, the effective attenuation of that line for TEM modes is then alpha equal to alpha D plus alpha C, and this we get its omega epsilon double prime over 2 eta plus 1 by B multiplied by that. So remember, that is from the conductors and that is from the dielectric. So, and this will increase with increasing frequency and decreasing plate separation. That is, as we bring the plates closer and closer together, this contribution from the finite conductivity of the conductors will increase, while This is increasing with frequency, and that is increasing with frequency as the square root, and therefore we say that both of them, the alpha will be increasing with frequency also. So plate separation cannot be made arbitrarily large. That is, if we want to reduce the contribution of the finite conductivity, then we may be led or misled to think that if we took the plates wider apart, the contribution from the finite conductivity of the conductors will become lower and lower. Okay, but then when we do that, the cutoff frequency of the first waveguide mode will become smaller and smaller, and therefore the bandwidth or the frequency range of useful frequency range of operation of our line will decrease, because we want most of the time this kind of two conductor plates lines we want to operate them in the TEM mode. Okay, and therefore we cannot make B arbitrarily large, because we have to think about the cutoff frequency of the first fundamental modes, the faster waveguide modes. So plate separation can also be not made arbitrarily small, because as we bring them closer and closer together, then the electric field between the plates will be increasing. And if it's increasing, it can quickly surpass the dielectric strength of the dielectric between the plates, and therefore the power handling capacity of that transmission line will be decreased. Okay, so we cannot make B smaller with arbitrarily. So for TM modes, the electric and magnetic field intensities for propagating modes with gamma equal to J beta is given by JK root 1 minus Fc by F all squared. And we saw that the axial field electric field component had a variation of En sine Kc of Y, where Kc is given by N pi by B, and for N equal to 0, 1, 2 to infinity. And therefore the transverse electric and magnetic field intensity are given by those expressions, which we just repeat here for convenience. So the time average Poynting vector is therefore going to be given P average equals to E of t cross H of t, and we get a value of omega epsilon beta by Kc squared multiplied by that value and the cosine squared of Kc y. And beta is in this case given by K equal to 1 minus Fc by F all squared. So for non-magnetic lossy dielectric, the propagation constant for the propagating TM modes will be given by gamma equal to J root K prime squared by minus Kc squared, where we are using this K prime squared as given by that value, which is the beta that we are dealing with. Okay, so and this is equal to omega squared mu epsilon prime into 1 minus J d sigma d by omega epsilon prime, where sigma d is the conductivity of the dielectric, and the Kc is going to be given by N pi by B. So, and therefore gamma is going to be given by that expression, okay, where we have separated the values, and then we can see that we can put them together in that form. This is the original in the case of a lossless case, and that is because of the finite conductivity. So, in other words, we can write this as J beta root 1 minus J omega mu by beta squared sigma d squared, where beta is now defined by that part that is the real part of the conductivity of the permittivity rather than the whole value, and we get a value of K root 1 minus Fc by N Fc of N F, where K is defined by omega root mu epsilon prime. So if beta squared is much larger than omega mu sigma d, then we can approximate this value. That is, we can expand this value in a binomial series, and we get a value of that nature. And thus, the gamma is going to be given by alpha d plus J beta And you see that this is going to be given by omega mu by beta sigma d by 2 plus j beta. And sigma d given by that value, that is when we replace the beta with its value, we'll get that equation, and we get another part for the propagation constant, from which we can see that alpha d will just be given by the real part of that gamma, and we get a value that is given down there. So if we look at this expression here, we can see that as we increase the frequency of operation, this factor here goes to unity, okay? And we expect that the alpha d will be increasing with frequency because of this f we have here at the bottom. So we note that alpha d will decrease with the increasing operating frequency. The TEM attenuation constant sigma d eta by 2 when loss is due to non-zero conductivity. So alpha d will increase with increasing operating frequency when the polarization or damping effects are present in the dielectric. And losses in the conductor will determine, the losses in the conductors will be determined using the energy conservation principle that we covered last time. We say that the rate of power loss at a plane z must be equal to twice or the energy or the power, the average power transported down the guide at that plane. So PL of Z is the loss in the conductors per unit length of line at Z, and PZ is the power propagating down the line at that value as well. And therefore, for a guide of identical plates of width W, that is identical in the sense that they are using the same material and the same width, then the P of Z is going to be given by W by 2, the integral of the average Poynting's vector, or the average Poynting's the power density over the cross section. Okay, here we are multiplying the cross section of the guide and then integrating between the plates, because you remember that E of Y is not uniform across the X direction or the B direction, and therefore we get a value of omega or W multiplied by that multiplied by K squared. And therefore these two will get another half here, and therefore you'll get a whole 4 down here. And that's why we have separated this as an amplitude divided by the square root of 2 for sinusoidal fields, so that we can see that this one now will be an RMS value, and we'll have another half this bottom. The surface current density at the bottom plate we saw was going to be given by the boundary condition on the tangential components of the magnetic field intensity, and we saw that that is going to be given by the magnitude of Hx at the y equal to 0, and that gives us a value of omega epsilon prime by Kc in n. And power loss per unit length of guide in both conductors will then be given by twice what we integrate there, and we'll get a value of 2 omega multiplied by that, which is multiplied by Rm, where Rm is of course the surface resistance per square on that conductor. Hence, the contribution to the losses due to the conductor losses will be given by the alpha C, which is given by that value divided by that, and we get a value of twice Rm by B eta into the propagation there. So this is just where we have taken out part of the constant, and we are having the frequency function in here. So alpha C for TM mode can therefore be seen clearly to increase with increasing operating frequency. That is, as we increase the operating frequency, the losses from the TM modes will start to increase. So for TE modes, the electric and magnetic field intensities for propagating modes will have the similar kind of propagation constant, and Hz or the axial component of the magnetic field intensity will be given by Hn cos the cosine of Kcy. Remember, the reason why we used a cosine is because the normal derivative of the magnetic field intensity must vanish at conducting plates. Or in other words, we can say that the tangential electric field components must vanish at the conducting surfaces. Okay? And therefore, since the Et is related to Hz through the special derivative, then we must have that Hz must have a cosine value, so that this E of t has a sine value at the surfaces. And therefore, these are the values that we obtained before, and I repeat them here for 4 coordinates. So the time average Poynting vector is therefore going to be given by that value for the lossless case, and the propagation constant will be the same as for the Tm modes, and hence alpha d will also have the same similar value. Now, power propagating down the guide at z is going to be given by P of z multiplied by Ex cross Hy star, and we see a value of that nature, which is a bit different from what we obtained for the Tm modes. And the power loss per unit length at z is therefore going to be given by that value there, and we get 2Whn root Rn. Thus, that becomes that the conduction losses, or the attenuation constant due to conduction losses, we therefore have that particular value. And we can see for our case, for TE modes, we see a very interesting case that the frequency, as the frequency increases, the operating frequency increases, alpha C decreases. We saw for TM modes, the alpha C was increasing with frequency, while this one is now decreasing. But then it will reach a point where it will start to increase as well. So we can say that for TE modes, alpha C tends to 0 as the operating frequency is increased. So we can plot the expressions for the attenuation constant for waveguide modes, okay, and we rearrange them with respect to the operating frequency to normalize to the cutoff frequency. That is, we put that dielectric losses for TM, for both TM and TE modes, we have alpha D equal to pi epsilon prime, double prime, f of c eta, and multiplied by f fc all squared, where fc of n is the cutoff frequency of the nth mode of the TE and TM modes. And this is the factor that is propagated there. So what we've been using 1 minus fc by f squared, but I've rearranged them so that we can make them easier to see in the plotting that I'm going to put down. Conductor losses for TM modes are given by that equation as well, and the conductor losses for TE modes will be expressed in that form, and for TM modes will be given that. Now we'll use a conductor with a plate separation of 2.3 centimeters for the n equal to 1, that is the waveguide modes. The conductors will then be assumed to be copper with a sigma c equal to 5.8 times 10 raised to that, and mu c, which is the permeability of free space, and a dielectric loss tangent for the dielectric about 10 raised to minus 5, and eta is therefore given by eta naught by root 2.3, which is the dielectric constant for the between the plates, and f of c has been taken to be 8.6 gigahertz. So the variation of the attenuation constant for waveguide modes is then going to be as shown here. So we have the dash dot curve here is for the TE modes, that is the attenuation constant due to finite conductivity of the plates. The dashed ones are those ones for the TM modes. The dark one here is the attenuation for the dielectric, and is the same for both TE and TM modes. And this frequency here has been normalized to the cutoff frequency of the first of the dominant mode in a parallel plate waveguide. That brings us to the end of that particular topic then. So I'm open for some questions if you have any. Any question? Okay, if there are no questions, then I'll give you a 5-minute break and we'll meet at the hour to continue with our topics then. So we'll continue from where we left. And now we look at the another attenuation now in the rectangular waveguides. I'm not going to cover any attenuation in the circular waveguides because, like we have talked, we are going to need to compute the Poynting's vector or the Poynting's average powers, and I don't want to go into the integration of Bessel functions at all. That one, the detail will lose everyone and it will serve no purpose. So we just look at the attenuation in rectangular waveguides because these are more commonly used in the industry, and we shall see why they are that popular. So the transverse electric and magnetic field intensities have, of course, given there as we repeat, and for TE modes, you have Kc equal to omega gamma squared plus omega squared mu epsilon, which is that value there, K, and we can always repeat it as pi by A root M squared by plus N squared A by B whole squared, and M varying from 0, 1, 2, and N varying from 0, 1, 2, with M and N not being equal to 0 simultaneously, for the obvious reasons that we already stated before. So, and for TM modes, we have Kc is similar to that, is the same, but the M and N all start from 1. There's no M equal to 0 or N equal to 0 mode. So we assume a copper hollow waveguide. Many times it will not be copper, it would be most of the times it will be aluminum because copper is very heavy and expensive. Or you could have copper coated with silver for very high, for the measurement labs, so to speak. So the dimensions are given as A by B, with A greater than B, and the wave propagation is in the Z direction by assumption, with a propagation factor given by exponent of j omega t minus gamma c. So the losses will be typically low in hollow waveguides, and the transverse field distribution can be assumed to be essentially the same as in the lossless waveguide. So the attenuation constant due to the dielectric losses will hence be given by the alpha d for the Mn mode will be given by sigma d, which is the conductivity of the dielectric, divided by 2, multiplied by the intrinsic impedance of that dielectric, and divided by the correction, the frequency correction factor, which we can always write it as that, and multiply it by F by Fc by Mn, where the cutoff frequency of the Mn mode is given by C by 2A root M squared plus N squared D by A whole squared. So electric and magnetic field intensities for propagating modes in a guide would in a guide will then be given by Hz equal to H1 0 cos Kc squared Kcx, and where Kc is just pi by A. That is for the TM10 mode. And the Ht was given by J beta by Kc squared, the special derivative of H of Z, and we get a value of that nature, and Et will have that sinusoid as well. Now, the reason why we are using the TE10 mode is because, like we said before, most of the waveguides that are used in industry will be designed for the propagation of the TE10 mode, which is the dominant mode in the, for rectangular waveguides. So, time average Poynting vector will therefore be given by the half, the real part of the transverse electric field across the complex conjugate of the transverse magnetic field intensity, and you get a value that looks of that nature, which is sinusoidal as well. So the time average power propagating down the guide, that is therefore will be given by the integral of the Poynting vector, okay, across the cross section of the guide. Therefore, we have to integrate from 0 to B and from 0 to A in the X direction and in the Y direction, and we are dealing with the wave propagating down the line, so it's in the projection in the along the axial axis, and we get a value that looks like that. And what we must note is that we have the cross section of the guide divided by 2. Of course, these 2 would come from the integral or the average of the sine squared Kc value there. So, or in other words, P of Z would be given by, when we replace beta and Kc squared with their values, what we'll get is AB by 2 multiplied by the intrinsic impedance of the dielectric multiplied by the RMS value squared of the magnetic field intensity of the 10 mode and multiplied by the frequency correction factor. The current densities in the 4 guide walls at x equal to 0 and A are then going to be given by Js of x at x equal to 0 is given by that value there, x cross z cap, hz of that, and we get a value of the minus of h10, and the Js of x equal to A is going to be given by that value, where the negative part would come, that is, we get a value of minus h10 coming from the cosine of pi. And therefore we see that at both at x equal to 0 and x equal to A, the current is flowing in the same direction, that is in the y direction. For the walls at y equal to 0 and B, we'll then have Js of y equal to that value there. And we see that we have 2 components because we have an axial z component of the magnetic field and an x directed magnetic field as well. And therefore we get a value of h10 of our next component with respect to sine and our z component that is proportional to k for the cosine. And at y equal to b, we get a similar value, and we get a minus value because of the cosine of the pi there. So, power loss per unit length of the guide at Z is hence going to be given by the 2 losses, that is the loss in the 2 walls at x equal to A and x equal to 0, and the 2 walls at y equal to 0 and y equal to B, where the PLX of 0 is given by that integral, and we get a value of B Rm H10 by root 2 all squared. And the PL of Y0 is going to be given by half of that value there, and we get a value of A by 2 H10 by root 2 and multiplied by F by FC 10 all squared. Because this, when you add these ones together, you get a value of F by C. And hence, the power loss per unit length of guide at Z is then given by the losses, the 2 losses, and we get a value of that nature, which we can always correct into that form by taking out the A and the F by FC by 2 squared. We take it out, and we get a value of that correction there, plus multiplied by A, F by FC and 0 all squared, and we get multiplied by Rm. And from the principle of conservation of energy, we then have that alpha C is going to be given by the power loss at Z over the twice the power propagating down the line at Z, and we get a value of that form. So, in other words, alpha C can be expressed in that form, which has been so arranged so that we can plot this easily on a graph, so to speak. That's why it's made this weird. It's not because we want to make life difficult, okay? But you can always get it at that level, and it will be okay. So alpha C from TE modes then decreases from a large value at F equal to approximately FC, that is when the propagation is not possible. So we have a big loss for the evanescent modes to a minimum value, and then it will start to increase again, and the operating frequency is increased. For guides with A greater than B, okay, which is made constant, the alpha C will decrease with the increasing guide height B, but cut-off frequency of the next higher mode will then be lowered. And useful frequency range before the next higher mode begins to propagate will therefore be made smaller, and therefore the guide will become less useful for us. So B cannot be made arbitrarily small, however, because if we want to suppress the next higher modes, we make B small, but we cannot make it too small because the fundamental or the dominant mode has the E polarized in the height direction of the guide, and therefore if we make the height smaller, narrower and narrower, what would happen is that the dielectric strength of the dielectric between the inside the guide will be exceeded, and the power handling capacity will be lowered. For TM modes, we shall consider the TM11 mode, and the electric and magnetic field intensities for a propagating mode is then going to be given by Ez equal to E11, the sine of pi by Ax, and the sine of pi by By. And therefore, E of t is going to be given by that expression there, and we get a value that looks like that. That is when we make the gradient of E of z. And the h of t, we get the z cross gradient of E of z, and we get that particular expression. So this, I'm not going into it so much, because once we have written like this, then the next thing we'll have to do is just the simple derivative differentiation of that expression. So I won't go into it a lot, because the differentiation should be straightforward. So time average Poynting vector is of course given by that expression there repeated, and we get a value that looks like that, and multiplied by k of x of y, where k of x of y is a function where the cosine and sine functions plus that direction for the other components. So time average power propagating down the guide at z will be given by the integral of the Poynting vector, or the average Poynting vector, over the cross section of the guide, and we get a value that has those two components, is very long. And when we complete that, because we have a product of cosine squared and sine squared, then we must have at least a half from the cosine squared and another half from the sine squared when we integrate over the guide dimensions. And therefore we have a 4 at the bottom here. So we get a value of P of z given by that expression then. Or in other words, we can write it as P of z equal to A by B, and multiply by that value when we replace beta and kc squared in expressions. Now, the current densities in the 4 guide walls are given by the Js of x equal to that, we get that value there, and the Js of x equal to A, we get that expression, which is the same as before. We just see that they are flowing in the same directions. Now, and at y, Js equal to y, we have that that expression, and for the y equal to b, we have that similar expressions. And again, we see that these are the same as well. So the in the walls, the currents seem to be flowing in the same direction for y equal to 0 and y equal to b, and in the same direction for x equal to 0 and x equal to b walls. So the power loss per unit length of guide at z is then hence going to be given by twice the power loss in the x equal to 0 plate, and the power loss in the y equals to 0 plate, where those values are given as shown. Okay, that is, we integrate the Js of x at 0 square by 2 Rm over the guide height, and we get that value. And the Pn of y equal to 0 is the integral over the guide width of that value at the bottom plate, and we get a value of at nature. And hence, when we add for the total power loss, we add it through, and what we can see is that it's related to that value with the AB, the cross section area of the guide multiplied by pi squared and multiplied by 1 by a cubed plus 1 by b cubed Rm omega epsilon by k c squared and multiplied by that value there. Or in other words, we can always change those values and we get that that is just the intrinsic impedance squared multiplied by that. So from the principle of the conservation of energy, we then now just take make the ratio PL of Z by 2PZ. And when we do that, we have already computed that. We have that. And then when we bring it down here, we just get a value of 2 to 1 plus A by B all cubed over 1 plus A by B all squared. And the square root of the frequency at the frequency factor multiplied by the Rm by A multiplied by that. Or in other words, we can see that alpha C can be corrected again, and we get it as a function of frequency all through. So when we express these terms to normalize the operating frequency to the cutoff frequency of the fundamental mode, then we'll get a value of alpha C equal to that value there. And for the TE10 mode and for the TM11 mode, we have that kind of expression where the Y is given by F by FC over 1 is the frequency normalized to the fundamental mode for the FC case, for the TM11 modes. And FC of 11, of course, will be given by that value, where we have an FC of the TE mode multiplied by that guide dimensions. So the attenuation constant due to the dielectric losses for the TE10 mode, of course, are going to be given by that expression. And for the TM11 mode, they'll be given by that expression as well. And you can see using the normalized frequencies as before, we have y squared by y squared minus 1 there, and that is x squared by root x squared minus 1 as well there. So we'll use copper walls, that is a copper guide, with mu of C given by that. The loss tangent for the dielectric is going to be given by 10 raised to minus 5. The A is 22 millimeters and the B is 10.1 millimeter. That is, and the 6.80 is the guide cutoff frequency for the F1 for the TE10 mode. So when we plot this, due to the dielectric at whatever and the conductor losses, this is what we obtain. So we see for the TM modes, the attenuation constant reduces from a very high value near F, near the cutoff frequency, and drops down towards a flat value, which is for the very high frequencies. Now, the alpha, that is the dielectric loss contribution for those, the TM modes, is again given there with a dash dot value. And here, for them to fit under between the same axis, I have reduced the values, the actual values of those attenuation constants by dividing by 1,000 here, and this one is divided by 1,000 as well for the TE10 mode. And we can see that this is increasing linearly, while for the TE10 mode, you can see they are increasing linearly, so to speak. So the theoretical formulae for attenuation are good in good agreement with measured values for frequency up to 5 gigahertz. For above 5 gigahertz, the surface roughness of the walls start to come in and will introduce other attenuation factors, okay? Other sources of attenuating the, increasing the attenuation in the guide. And therefore, these values have assumed that the surface roughness is that the walls are very smooth, and therefore the propagation or the current flow is not hindered in any way. So for higher frequencies, we can say that the measured values are generally higher depending on the guide surface smoothness of the walls. So when the roughness is on the order of the skin depth, at the operating frequency, the effective surface area that will be seen by the conducting currents or the flowing currents will be increased, and the losses will therefore increase. And this may explain the higher attenuation values that would be usually measured in such kind of guides that operated at high frequencies. Example 1. A TE10 mode wave at 10 gigahertz is propagating in a brass rectangular waveguide with either dimensions A equal to 1.5 centimeters and B equal to 0.6 centimeters. If the dielectric is polythene with E epsilon equal to 2.25, mu r of 1, and loss tangent of 4 times 10 raised to minus 4, determine A, the phase constant and guide wavelength, B, the phase velocity and wave impedance, and C, the attenuation constant due to loss in the dielectric, the attenuation constant due to loss in the guide walls. So this is a guide walls rather. And you are required to take the conductivity of the brass as 1.57 times 10 raised to 7 unit per meter. So the wavelength in an unbounded polythene is going to be given by lambda equal to c by the frequency, okay, the velocity, the phase velocity in the polythene by and divided by the frequency of the wave, and we get that the c is defined here as in gigahertz centimeter, where the gigahertz stands for the 10 raised to 9 per second, so that we can easily cancel out values and get the correct dimensions of the guide or of the quantity being measured. And therefore, for this particular case, we have that the lambda is 2 centimeters, and the cutoff frequency of the fundamental mode is going to be 6.67 gigahertz. Beta is going to be given by omega divided by the phase velocity, and we get that the root is going to be given by 1 multiplied by the root of 1 minus fc by f, and we get a value of 74.5 pi, or 234 radians per meter. And the lambda, the guide wavelength, is going to be given by the free unbounded polythene guide wavelength divided by the correct frequency correction factor, which at the operating frequency will give us a value of 0.0268 meters, or about 26 millimeters. B, we get Vp is going to be given by the velocity over the frequency correction factor, and we get a value of 2.68 times 10 raised to 8 meters per second. And the intrinsic or the characteristic impedance for that, or the wave impedance for the TE modes is going to be given by that value, which is given by 333.4 ohms. So the attenuation constant contributed by the dielectric, we are going to use a loss tangent of as epsilon double prime over epsilon prime, or sigma conductivity of the conductivity of the dielectric divided by omega epsilon, and we have a value of that given by omega epsilon, the tangent of delta, and multiplied by that value there. And we know that this value, we have been given the loss tangent, so the only thing we need to do is to multiply omega epsilon with the loss tangent, and we get a value of the conductivity. And therefore, the contribution or the attenuation constant for the dielectric is going to be given by that sigma for the dielectric divided by 2 and multiplied by the intrinsic impedance or the characteristic impedance for the TE modes. I'm calling it characteristic impedance, but it's called the wave impedance for the TE modes, and we get a value of 0.084 nepers per meter. Usually in industry, the attenuation constants are given in terms of dB per meter, and therefore we just divide that by 8.686 nepers per dB per, what is it called? Nepers per dB, or dB per meter per neper, to get the value of that. That is, multiply that one by 8.6686 dB per NEPA, so to speak, to get that 0.73 dB there. And D, Rm is going to be given by about 0.05 ohms, and therefore the because of the conductivity, we get a value of that nature there, which is 0.526 dB per meter. Example 2. A length of an air-filled copper X-band waveguide has dimensions A equal to 2.286 centimeter and B equal to 1.016 centimeter. Find the cutoff frequencies of the first 4 propagating modes and hence determine the attenuation in dB of a 1 meter section of guide operated at 10 gigahertz. Usually, you may get this value. You are being told X-band waveguide, and then you ask yourself, what the heck does X-band mean? So usually, for the X-band, of course, is the frequency range between 8 gigahertz to 12 gigahertz, but you don't really need to know this. That is, the X-band is just showing you which frequency range that guide is useful for. Okay, but you are for computing everything that you need to compute here is just that value, those values there, and the cutoff frequency of the guide, and you know that you cannot operate it below that value, so to speak. So immediately, the cutoff frequencies of the first 4 propagating modes will be given. We know that the expression for the cutoff frequency is given by that. And thus, we can have that. For those of us who already did the exercise I gave, that is, you made the table for the frequencies, that is, for the rectangular guide frequencies, you will get that easily. And therefore, you can see that as M and N varies, we have for the TE10 mode being the dominant mode with a cutoff frequency of 6.562 gigahertz for that particular guide with those dimensions. The second mode to propagate will be the TE20 mode, and we have a frequency of 13.123, and that's why our guide is called an X-band waveguide, because it's usually operated at 8 gigahertz up to a maximum of 12 gigahertz. So it's within this range here. And the TE01 mode is the third, followed by the TE and TM modes of the 1-1 range. And these TE and TM modes are now called degenerate because they have the same cutoff frequency. If we operated our waveguide at, say, a frequency of 17 gigahertz, all these modes from TE10 to TM11 modes will be propagating. The TE12 and TE and TM21 will be much higher. That's what we mean. But we can see that this should be, of course, the interchange here. This one is lower than that. It propagates before that 1-2 mode propagates. The cutoff frequency or the propagation constant for the TE10 mode is, of course, given by that value, which is 158.05 per meter. You could put there radians per meter, but we are not putting radians because radians anyway is a dimensionless quantity. Just put there for fun. So sigma copper is given by 5.8 times 10 raised to 7 million per meter, and Rm is given by that value. And therefore, alpha will be given by those values that we have already computed before, and we get a value of 0.0125 nepers per meter, or an attenuation of 0.11 dB. And that brings us to the end of that particular section. So, any question then so far? Is there a reason why you are so quiet?
No reason.
Yeah. So when I I don't know whether you are working on the tutorials that have been made available to you, and I'm sure when you are dealing with whatever the transmission lines, I don't know whether any of you have seen them. Now that I didn't understand that question you just said when you talked about circular, and I don't know what circular you are meaning. So maybe perhaps you could elaborate what it is you're saying. Wambua Michael, what is it you meant to ask? Wambua Michael, or he disappeared? You have an issue with your, but if I guess what it is you are trying to ask, what I said is that for the circular waveguides, we have seen that the fields operate or have the base of functions. The base of functions, they are proportional to base of functions, and when we are trying to talk about power propagation through these guides, we have seen that we must compute the time average Poynting's vector. And then to get the powers, we have to integrate over the spatial dimensions of the guides. And what I meant is that having to integrate base of functions is not a very interesting thing. That one is only done by guys who want to go to hell. So I didn't want to go into that, and I wanted to just show the simpler terms, because what we wanted to understand is the attenuation, the concept of attenuation due to the losses in both the dielectric and the guides. That's the only thing I was meaning about the complexity of it. But in the industry, of course, if you are interested in computing the attenuation constant of a given, say, guide of a given cross section, then you may have to do it. But what happens is that because of those integrals being complex, they are usually provided in a handbook, so to speak. So all you need to do is to go refer to the handbook, and you can do that quickly. But for the rectangular waveguides, it's easy to integrate, and therefore we were just doing it to show that's the same thing. That's the same process you have to go through when you are dealing with the attenuation in circular waveguides as well. It's only that the integrals are a little bit more complex there. I hope that answers your question. So what I was saying is that when you deal with those tutorials in transmission lines, there is one important thing you have to remember, that you are going to get cosine and sines, real and imaginary parts. And usually when you are computing, the imaginary part may be negative or positive. The real part also may be negative or positive for the impedances. And therefore, the angles that you are dealing with will have to be treated likewise. And therefore, if you take the tangent, the way you are used to working with complex numbers is that you get the magnitude by squaring the real and the imaginary part, adding them up and taking the square root. Then for the angle, you get the imaginary part divided by the real part, and you get a tangent value. Then you take the arctangent. Now, what happens is that if the imaginary part is negative and the real part is positive, you have no problem, because the tangent has a period of pi, and therefore you can get plus and minus angles. But if the real part is negative and the imaginary part is positive, then you'll find that that angle will not be the negative of what you'll get by dividing the real part and the imaginary part. That is the imaginary part over the real part. But it will be an angle that is greater than 90 degrees. So it will be an angle that is less than 180 degrees. The best way you can deal with it is to multiply through what the impedance you are trying to convert, multiply through by -1, and recall that multiplying by -1 is like increasing the angle by pi, because -1 is just equal to exponent of minus j, okay, j pi, okay, or j pi, exponent of j pi if you like. And therefore all you have to do is that once you divide and you get the arctangent, which is a negative, you must add it to 180 degrees, then you get an angle between 180 and 90. If you get both the real part and the imaginary part are negative, if you do a straight division of real part by imaginary part by real part, imaginary part by real part, you'll get a positive tangent, but that is not the angle. And therefore, you must remember to add 180 degrees to that angle. Therefore, it will be an angle between 180 degrees and 270. So that's the thing you have to think about when you are working with these transmission lines, especially using the usual analytical methods. Why I'm saying this is because many of the times you'll be trying to look for the length of line, and you may find that you are getting very weird looking lines, and it's that one will just come because of not taking the correct into consideration the period of the tangent function. Another way you can deal with it is, of course, to use the long method. That is, you get the modulus of the quantity you are trying to convert, and then you can therefore start using, like, you know that the cosine will be the real part divided by that magnitude, and the sine, the imaginary part will be divided by the magnitude, will give us the sine of the angle. So that's, you can deal with it that way. But many of the times is that most of the time we will always use the division of the real part by the imaginary part by the real part, and take the arctangent. And when we do this, remember that the tangent has a period of pi, while the cosine and sine have periods of twice pi. Okay, so it's up to you to decide which one you'll find easier to use for that particular case. So I'll introduce now what we are meant to look at next, and this is what we call the dielectric waveguides. We said that at high frequencies, we shall see that it's also possible for us to guide power through the dielectric. If you look at the transmission line, and having perfect conductors, the electric field inside the conductors is going to be equal to 0, and therefore the magnetic field is also going to be equal to 0. But we have said that power propagation is simply the cross product, is given by the Poynting's theorem, and therefore when we take the cross product of the electric field and the magnetic field inside the conductor, we should get 0. But we are all sure, and we know as a fact from the lab and otherwise, that if we connected a resistor to a power source, whether AC or DC, that resistor will absorb power or energy from the power source. But how does that power then get to the resistor if it's going to be equal to 0 inside the conductor is equal to 0? What you should note is that power propagation in all guiding structures is propagated through the dielectric and not the conductors. The conductors are there to guide the waves to where they are going to be absorbed, and nothing else. Okay? So therefore it means we can do away with those conductors and just deal with the dielectric alone, and we should be able to convey energy from one point of this of space to another point, okay, without the conductors. But why? How can we do this? So the cross-section of an inhomogeneously filled parallel plate transmission line would be as shown below. Here we have plates that are wide. We are not giving the width. Could be a width W that is much larger than the height, which is B, or the plate separation. And we have a dielectric of thickness A placed on the bottom of the guide, okay, on the bottom, placed on the bottom plate of that transmission line. And then it does not completely fill the guide cross section, okay, and therefore we have part of the region has the dielectric and part of it has air as the dielectric. Now, what we are saying is that it's possible for us to just take a value or a width or a guide of width 2W, okay, and treat it as a parallel plate transmission line and in our computations. So the plate separation is B, and the thickness of the dielectric is A, and the dielectric rests intimately on the bottom conducting plate, which we shall call the grounded plane or the ground plane. So the plates will be assumed to be perfectly conducting, and they are also of infinite extent in both the Z and the X direction. For low frequency of propagation, then we see that this will be similar to that of the dielectric field two-plate line, and characterized by a phase of propagation constant of beta equal to omega root L prime by C prime, where L prime and C prime are the per unit length inductance and capacitance of that particular plate. At higher frequencies, beta will be increasing faster than omega, and the line will therefore be dispersive. So we shall show the following discussion that there exists a surface wave mode of propagation in the vicinity of the air and dielectric interface. So in analyzing the transmission line, we applied a magnetic wall, where we remember that the magnetic wall was where the tangential components of the magnetic field intensity vanish at the wall, while the electric field will be everywhere tangential to that wall. Now, the boundary conditions for the fields on a magnetic wall or a perfectly conducting magnetic conductor, which we usually call PMC, are that the tangential component of the magnetic field intensity is going to be 0, and the normal component is 0 as well. Of course, this coming from the Gauss law for magnetic fields, and the tangential component of the electric field intensity is equal to the charge, the surface charge density divided by epsilon. This is not right. This should be dotted rather. Okay. So a PMC can be safely inserted along a plane for which the tangential magnetic field is equal to 0, and we will not disturb the field at all. And that's why we have the following kind of thing. So the magnetic walls are placed here, are those walls for that particular case. So such a plane will then correspond to certain symmetries in the planes in a given field problem. So we'll assume a Y-polarized wave propagating in the Z direction between the plates and with the fields having no variations over the X direction. That is, they are uniform along the X, but they are varying in the Y. And hence, only the EY, the EZ, and HZ will be non-zero. And this then will allow us to place a magnetic wall along any X equal to a constant plane without disturbing the field. So in the present case, we could choose planes that are at X equal to plus or minus W as shown, and the problem can then be treated as a waveguide structure with electric walls and the conducting plates at y equal to 0 and b, and magnetic walls at x equal to plus or minus w. And in an ideal transmission line, the propagation constant will be equal to that of a plain TEM wave in the surrounding medium. And since the situation in the present problem is an uniform one, then we can anticipate that beta will have an intermediate value between its value in the air region and the dielectric region. That is, we should have beta lying between the propagation constant in air and the propagation constant in the dielectric. So at a charge-free point between the plates, Ez is a solution of the transverse Helmholtz equations of that nature, in the dielectric region, and that will be the case in the air region, where the Kd squared is equal to K squared minus beta squared in the dielectric, and Ka squared is going to be given by K naught squared minus B squared in the air region. Remember, the Kd and Ka represent the Kc's that we've been dealing with in the other cases, only that we are saying Kc is equal to Kd in the dielectric region and Kc equal to Ka in the air region. And the general solution will therefore be of the form E1 sine k dy plus E3 cos k dy there. And for Ez in the air region, we have E2 sine Ka y minus b plus E4 sine cos Ka y minus b, where E3, E1, E2, E3, E4 are just amplitudes which must be determined from the boundary conditions on the, imposed on the fields. So we'll note that the continuity of the tangential components of the fields across the air dielectric interface will require that beta be the same in both the air and the dielectric regions. Thus, at the interface, we must have that Ka squared minus K naught squared is equal to Kd squared minus K squared, or in other words, we must have epsilon r minus 1 multiplied by K naught squared must be equal to Kd squared minus Ka squared. That is called a dispersion expression. And since Ez is equal to 0 at y equal to 0 and y equal to b, then we must have that E3 and E4 are all 0, and therefore we have that Ez is equal to E1 sine k dy in the dielectric region, and Ez is equal to E2 sine Ka y minus b at inside the air region. So the continuity of Ez across the interface at y equal to a will then allow us to write that E2 is equal to the minus of E1 sine k dA over sine Ka b minus a, well, this is equal to that value there. Okay, where d has been expressed as b minus a. So hence, Ez is going to be given by that value, and Ez is going to be given by that value inside the air region. So for the transverse fields, we have that from the reduced Maxwell's equations. We can get it as the gradient of the Ez, and we'll get those in the air, in the dielectric, and that expression in the air region. And the magnetic fields will have that in the air, in the dielectric region, and the expression will be of that nature in the air region. Remember, we are only doing the spatial differentiation of Ez, and therefore these expressions, although they look complex, they are easily obtained from simple differentiation. The continuity of the magnetic field at y equal to a will then give us a value for those values there, and we get an equation which is a tangential equation. This is called a transcendental equation, which has a value of epsilon r multiplied by Ka, tangent of Kad equal to the minus of Kd tangent Kda. And there is an infinite number of solutions for Kd and Ka that will satisfy those equations, and an infinite number of E modes will therefore be possible in that guide. So most of the modes will, however, be evanescent because beta is given by k naught squared minus ka, and this must be equal to k squared minus kd squared in the dielectric. And we must have that ka is less than k naught and kd is greater than k. For beta to be real, that ka must be a lot smaller than k naught. And thus, for beta lying between k naught and k, ka must be imaginary, that is, it must be complex. Say ka equal to the minus of j alpha, where we are using this deliberately so that we can have a similar expression as that we are familiar with, that of attenuation. And hence, we must have that kd, the tangent of kdA, must be equal to alpha multiplied by epsilon r multiplied by alpha, and the tangent of alpha d. And kd squared plus alpha squared is equal to epsilon r minus 1 k naught squared. So these are two equations. This is the dispersion equation, and that is the transcendental equations that obtain from the boundary conditions. So what we do is multiply that one by the size of the dielectric, that is d and a, and we can get the we can solve this graphically. So for very low frequencies, k naught squared is very small, and both kd and alpha will be very small as a consequence. And therefore, we can have that the tangent of kdA will be approximately kdA, and the hyperbolic tangent of alpha d will also be given approximately by alpha d. And hence, we have that kd squared A equal to alpha epsilon r alpha squared d, or in other words, we can get a value for alpha squared as epsilon r minus 1 k naught squared multiplied by A plus epsilon r multiplied by d. Remember that d is the height of the air region, and A is the height of the thickness of the dielectric. And hence, we can then have that the beta is going to be given by k naught squared plus alpha squared, which is equal to k naught alpha rb over A plus epsilon r d, which is equal to k naught and multiplied by an effective dielectric constant for the dielectric, and this effective dielectric constant is of course given by that value there. And kd is going to be given by k naught into epsilon r minus 1 d over A plus epsilon r, and we can therefore have that. So if the current density Jz on the inner surface of the upper plate is uniform, then the magnetic field between the plates will be given by Hx equal to Jz for an electric wall. And thus, the time average energy stored that integral, okay, giving us a value of 1 by 4 the L prime by Iz squared, where Iz squared is Iz is given by 2 multiplied by W and multiplied by the surface current density. Okay, so we see that L prime here is of course an inductance per unit length, and hence we see that L prime is just mu naught B over 2W. The capacitance per unit length can be regarded as two series capacitances, one for the dielectric in series with one with a parallel plate with air as a dielectric. One for the air region is C air prime, which is given by twice epsilon naught W by D, and one for the dielectric, which is twice epsilon R epsilon naught multiplied by W by A, and we add them together so that we get that the total capacitance per unit length is going to be given by that addition, and we get a value of that nature. And therefore, if we get the product of L prime by C prime, we get a value of that level. So at low frequencies, we can then, of course, write that E2 is approximately going to be given by the J E1 KdA by alpha D, and hence, in the dielectric region, we have Ez is approximately E1 KdY, and EY will have to be given by that expression there, and EX by a similar value. And in the air region, we have Ez given by that, and the EY and EX, HX are given by those expressions, where we are just using manipulation of the given parameters. So we note therefore that the axial electric field component will tend to 0 as both K0 and Kd are made to vanish, while the Ey and Hx will remain constant. And hence, this means that as Ez is, as the K0 and Kd are reduced to 0, and remember, K0 and Kd going to 0 means that the wavelength is being increased of the signal, and therefore we are going towards DC. And we can see that the TEM situation now propagates inside that parallel plate, partially filled parallel plate transmission line. So if V is defined as the negative integral from 0 to A in the dielectric plus the integral of the electric field from A bit in the air region, then we'll have a value of that nature, that V is going to have a complex value, and the total Z directed current is then be given by twice W multiplied by Z. And hence, the wave impedance for that that parallel line or that parallel plate line will be V by Iz, which is equal to that value over that, and we get a value of root L prime by C prime, which is the TEM case. At high frequencies, K0, Kd, and alpha will be very large, and therefore alpha D will also be large, and therefore we can say that the tangent of alpha D will go towards unity. So we therefore have, remember that the hyperbolic tangent is the hyperbolic sine over the hyperbolic cosine. And if we were to look at that, if we were to expand those ones into the exponent, we'll see that only the exponent of alpha D will be large as alpha D goes to, becomes very large. The exponent of minus alpha D will go to 0, and therefore the hyperbolic tangent and the hyperbolic cosine will be equal, approximately equal, for alpha D large. And therefore we can write that for the transcendental equation, that we have a value of Kd, tangent of KdA equal to approximately epsilon r alpha, which is that value there. And we see that now at higher frequencies, this becomes independent of the plate separation, and it means that we can take the top plate to infinity without violating the propagation of high frequency fields between on that line. So we can therefore say that the top plate can therefore be allowed to recede to infinity, and we will not affect the high frequency solution that we have obtained here. And that therefore gives us an axial electric field component that has a value of E1 sine k dy in the dielectric, and an EY given by sine k dA exponent of alpha y minus A in the air region. And since B has been taken to infinity, then we can see that this being positive and y being greater than A, then this value will become, what is it? This value becomes much smaller, so to speak. It will become, will be increasing, so to speak. And we must therefore have certain assumptions. So we shall make the following. So E will decay away. I think it's a negative sign that is missing here. I'm missing a negative sign for this particular value for us to get the value of that. So thus Ez decays exponentially away from the air dielectric interface and will be independent of the split separation as long as alpha D equal to alpha B minus A is large. So as B goes to infinity, the field will be guided by the dielectric sheet and is a surface wave because it is confined to the region close to the dielectric surface. And the first root for Kd will then occur when Kd of A is less than pi by 2, And as K naught goes to infinity, Kd will remain bounded, but beta squared will also tend to infinity. And hence, at sufficiently high frequency, Kd squared will be much smaller than K naught squared, and beta will therefore be approximately the propagation constant of that wave inside the dielectric. And therefore, we can say that the field is confined within the dielectric alone. Therefore, beta will vary from a low frequency value of K naught multiplied by epsilon effective to an asymptotically high frequency value, that is K naught multiplied by root pi, that is the K in the dielectric. And since beta is a linear function of omega, the line is still dispersive. So the second wave mode will occur when Kd is between pi and 3 pi by 2 for K naught greater than pi. And we note that there are other solutions with a real value of alpha, where n is an integer for which beta will be imaginary, and therefore there will be no propagation. And hence, the modes will be evanescent as long as pi by b is greater than K naught. The cutoff will occur when alpha is equal to K naught, and therefore beta is going to be equal to 0. And thus, we must have that for cutoff. That will be the equation to satisfy. And since Kd is equal to K, with beta equal to 0, then that value should be obtained, and we can get a solution of that nature. So we'll plot the tangent equations. Those are the tangent equations. And that circular part is from the dispersion equation that we obtained, beta squared equal to whatever, the dispersion equation that we got. And where the two curves intersect represent the solution. And therefore, we can see the next solution will be for those values that for a circle with a radius such that it cuts the other branches of the tangent curve. Remember, these dashed signs, we don't want this value to be, this value should not be equal to be, should not be negative, and therefore these are not solutions. So the only solutions are for the positive value above the curve. Okay. So I think now I'll stop at that point, and we'll look at now at the dielectric slab when suspended in air, because this is what would happen for, say, a fiber optic. But we shall not deal with a round fiber optic. We shall deal with a rectangular slab, or a slab of dielectric, for easier computation. But remember, the fiber optic is actually round. So my time is up. So I wish you a peaceful Easter. In case you have any questions, you can ask now, or we can stop there and we meet next time. There is a question of how low does the frequency decrease until it is considered DC? Well, that one is a good question. You remember we talked about what DC is and what AC is just a matter of conjecture. Of course, DC, you say there is no variation, in time. So what we are saying is that as long as the wavelength of your, or the frequency of your, what is it, the wavelength or the frequency, how should I put it? What you are dealing with is the variation. Say, for example, for a microwave engineer who deals with gigahertz, a frequency of a few kilohertz, that one is, as far as is concerned, is DC. That is, if you are dealing with microwave systems, they are usually so small that the wavelength itself is very large compared to the components we are dealing with. And that's when we start saying that we are dealing with the DC level. So what I can say is that you really can't use the frequencies to determine what DC is. It's a relative kind of thing. It depends on the application, I would say. By the That is, the time variation is very, very slow compared to the other values that are the changing values that we have. I don't know whether that one makes sense, because I feel like speaking in convoluted language. Okay? So for example, you have dealt with signal processing. Yeah, Wambua. Yes, you have dealt with that. Now, you know that say for example, the Earth, if I want to put it like in geological terms, the Earth is actually precessing about the poles, and the period of a pole of that precision is usually about 72,000 years. So as far as we are concerned, it's a constant. The same thing, the sun is also rotating about its axis, but it takes about, I think, several weeks before it actually completes one. And therefore, as far as we are concerned here on Earth, it could be assumed to be stationary. So whether it's DC or AC, it depends on the relative, that is the changes, the time changes relative to what you are dealing with at that particular time. Okay? Agreed. So for example, if you have a DC signal, it doesn't have a time variation. And therefore its period is going to be infinite. What is the length of time you have to wait before you repeat the same value? You have to wait infinite time. Then we call it DC. You may wait, say, several years for it to get back to the same value you have at that particular time. That will be a slowly varying signal. And therefore, if you have signals that are varying on shorter time scales, then those ones will be called AC, while these ones with longer time scales will be called DC. So any other question? So I wish you a safe and peaceful Easter. Then let's meet next week then, in case there are no more questions.
Thank you.
Okay, yeah, welcome.